Okay, so in last class we spoke about the hydrogen atom spectra, which all of you are of course familiar with. So now we have a question about R infinity, what it means. Okay, so the thing is that this first equation here, this is for just the hydrogen atom. So this is what was done by Rydberg originally. And RH is an experimentally determined constant with this value. Okay? So this is what Rydberg determined. However, it can be extended to hydrogen-like atoms. So by hydrogen-like atoms, I mean where the atom has one electron, but the nuclear charge can be something else. So you can have helium plus, lithium 2 plus, beryllium 3 plus, etc. So the nucleus is becoming heavier with atomic number Z, but the electron there's only one electron. Okay. In that case, the Rydberg constant changes. Okay, and how do you determine this Rydberg constant? Then you need another sort of universal constant, R infinity. So this is theoretically determined. Okay, so this is a universal constant multiplied by 1 minus me by capital M, where capital M is the total mass of the atom. So this changes for the various atoms, and me is the mass of the electrons. And this theoretically determined universal constant, R infinity, this can be thought of to correspond to a hydrogen-like system with infinite nuclear mass. So you see, if you put capital M equal to infinity, then Rm is equal to R infinity. So it's the Rydberg. So it's a way of defining it in hindsight. It's a theoretical universal constant, and you can identify it with the Rydberg constant that you would have had if you had a hydrogen-like atom where the nucleus is of infinite mass. Does that clarify things?
Thank you, ma'am.
Yeah.
Ma'am, I also have a question.
Yeah, go ahead.
Hello?
Yeah.
On slide 24, could you go there?
24. This one.
Yeah. The one where it's like EV naught and stuff like that, isn't it?
The photoelectric effect. This one? No.
Just below the plot.
Okay. So this the slide number that is coming up here is different from.
Oh, sorry.
Yeah. No problem. Yeah.
So could you explain this one, like this point V is equal to V dash naught, and then like when with energy greater than EV, it can arrive at an anode with potential V. I didn't really understand that.
Okay, so let me just go back a little bit and then show you the plot, and then it will be easier to explain. So I'm changing the applied voltage. Let's just concentrate on one plot, okay? Let's say this one. So I have this photoelectric current measurement system set up, and I have first a positive voltage. So as long as I have a positive voltage, then any electron that is emitted from the cathode, from this metal, that is collected by the anode. So you have a constant current. So as even if it is a little bit positive, you get all the electrons. Even if it is highly positive, you get all the electrons, because the electron gets accelerated towards the anode. And okay, now once this potential becomes negative, then the anode repels the electrons. It doesn't want to collect them. However, as long as the kinetic energy of the electrons, which is this one, energy, is greater than the repelling energy, or the repelling voltage into the charge of the electron, those electrons can still reach the anode because they have more energy than the repelling energy, if I say it like that.
Okay.
But as you increase this repelling voltage, then the number of electrons start falling because not all the electrons are as energetic. So the slower ones, or the low energy ones, they cannot reach slowly. So then the current starts falling, the photocurrent.
Okay, but when we're talking about like negative voltage or positive, isn't that like kind of all relative? So then how can we decide from that?
You mean relative? Yeah, it is relative. So it is relative to the cathode.
Okay,
So
okay, got it. All right.
So you got it.
Thank
So the
you.
current falls, and eventually even the most energetic electron will not be able to reach the anode, and that voltage is stopping potential when you get zero current. So
Okay,
okay,
yeah, got it. Thank you.
got it. Okay, no problem. Then so today we will do the Compton scattering. So I mentioned it last time, but let's do it in greater detail today. So I'll do the derivation. That is here. Okay. So in the Compton effect, what we have is, so this is a model, okay? So the model is that you have a free electron, which means that it is free to move. Okay? And then you have a high energy light. So typically an X-ray that falls on this electron. Okay? And then what is observed is that the X-ray gets scattered. Okay? And so does the electron. So both get scattered. And let's call the angles theta and phi. So this is the setup. And the observation is that the two X-rays, the incident X-ray, if I say it has a frequency nu 0, then the scattered X-ray is found to have a different frequency nu, and this nu is found to be less than nu 0. Okay. So nu less than nu 0. And the electron, of course, it had zero momentum before, but it gains a momentum Pe. I'll also write the momenta for the photons. So the X-ray photon has momentum P0, the incident X-ray photon, and the scattered one I'll call P. Now, by momentum conservation, in the X direction, so in this direction, I had P0 before, and finally I have P cos theta plus PE cos phi. So this is for the X direction or whatever. And then for the perpendicular direction, I had zero momentum before, but now I have P sine theta minus PE sine phi. Let's call this equation 1 and then rearrange this. So sine theta is equal to then PE by P sine phi. And maybe I might need sine phi as well. So sine phi is equal to P by PE sine theta. So let me call, okay, I'll label that later. So this is this. So then I can replace either theta or phi. I'll choose to replace phi. and keep theta. And I will write P0 as PE root of 1 minus E by PE sine theta squared plus P cos theta. So P cos theta has remained as it is, and PE into cos phi I have written as root over 1 minus sine square phi, which is this. Okay. I'll call this equation 2. Now we know that P is equal to H by lambda. So I have not introduced this relation yet, but this was used to explain the Compton effect. So I'm doing it now, but I will talk about the implications later. So this is de Broglie's equation. No, wait, 1 second. So P was the momentum of the X-ray. Oh no, sorry, this is not de Broglie. This is just Einstein's quantization. So this is for the X-ray. So this just tells you that the photon has momentum P, which is given by H by lambda. And P is this, and this you can also write as lambda, you can write as C by nu. So C by nu, H nu by C. Now we will replace then, and then okay, and P0 is also then H nu 0 by C. Therefore, from 2, we have H nu 0 by C is equal to PE root over 1 minus P squared by PE square sine square theta plus.
Ma'am,
Yeah?
ma'am, can you please go to the model diagram one?
Yeah.
Ma'am, here that mu for different electron is same, right? So, after deflecting,
Nu for electron. Okay, so we are just considering the momentum for the electron. If we talk about the wavelength and frequency of the electron, then yeah, it will gain something. So it was 0 before because the electron was not moving. So you will have some wavelength that the electron gets if you want to do that. But for Compton effect, it's enough to talk about the momentum of the electron.
okay, ma'am. Basically, so means X-ray is striking the electron, and electron is getting deflected, and at that side, means X-ray is going there, or
Yeah, so the light is getting sort of deflected, electron is also getting deflected, but
okay,
the deflected light has a different frequency from the incident light.
okay, ma'am. Okay, got that.
Yeah. So this is it. So this is the equation we get from momentum conservation. Call that 3. Then the next thing we will use is energy conservation.
Ma'am,
Yeah.
which was the first equation?
The first one was this one, the
Okay.
x direction.
Okay.
Conservation of momentum in the x direction. Okay.
What is the difference between Einstein's quantization and de Broglie's wavelength? I don't
De Broglie's deals with the matter waves, so the wavelength of particles, and Einstein deals with the quantization of the momentum of radiation or light. So actually today we will talk quite a lot about it. So
Okay.
it will be clear. Okay. So energy conservation is simple. So you have the X-ray plus electron at rest, and that is giving you scattered X-ray plus scattered electron. So we have to find out the energy of each of this. So the X-ray had energy h nu 0. The electron at rest had energy 0. Then the scattered X-ray has h nu, and the scattered electron has an energy EE. I'll write it as EE for now. EE is, you could have just written half mv square or p square by 2m, pe square by 2m, but that would have been the non-relativistic expression. So if I wrote it just as p square by 2m, this is non-relativistic kinetic energy. Unfortunately, the non-relativistic kinetic energy of the electron is not enough to give you a good description of the Compton effect. So what we will use is the relativistic energy expression, which is E squared is equal to Pe squared C squared plus Me squared C to the power 4. So this is the energy. So the first term is the energy coming from motion, kinetic energy, and the second term comes from the rest mass of the electron. So this is the relativistic energy of the electron. Okay. This is kinetic energy, this is mass energy, if you like.
Ma'am, so shouldn't there be the same term in the left-hand side in the electron at rest?
Yes,
MEC square.
Yes, it will be there. You are right. So when I go over to the relativistic expression, then even the rest mass energy will be there even for the electron at rest. Yeah, thank you. So then let's write the conservation of energy once more. So that's h nu 0 plus MEC square is equal to h nu plus EE, and this I will call 5. Okay. Now from 3, let's just type in h nu 0 is equal to h nu cos theta plus PEC and then h 0 minus h nu cos theta equal to theta. So this, and then square 6.
Ma'am, we can't see what you're writing.
Because it's small, or
No, ma'am, the
No, ma'am,
video is
it's
lagging.
lagging.
lagging. Okay. Let's just wait a second.
Ma'am, both the audio and video is like.
Audio is good, I think.
So let's just wait like few seconds. I've written squaring
Fine.
6. Yeah, tell me when you can see that.
Ma'am, have you only written squaring?
So I've written squaring 6 and now I'm writing the next one very slowly.
Oh, okay.
Yeah, can you see the equation? So I've written one more equation after squaring 6.
Yes.
Okay. So then maybe the lag is better. So now I'm just doing some algebra. So even if it lags a little bit, you will be fine. Okay. So I've written equation 7, and then I will now use equation 5. I'll just rearrange it a little bit. I will put the h nu terms on one side. H nu 0 minus h nu e n e c squared. And then I will square this as well.
Hello, ma'am.
Yeah.
Ma'am, in equation 6, you have squared here, so won't it be cos squared theta?
Ah, yes. This will be cos square theta.
Ma'am, shouldn't we keep just EE on the RHS to square it, because that will help get rid of the square root?
Well, I want to compare 7 and the squared form of 8. So
Okay.
this is more useful. Okay, so squaring 8. H squared mu 0 squared plus 8 squared mu squared minus 2 squared mu 0 mu. This is equal to EE squared plus ME squared c to the power 4 minus 2EE ME c squared. Okay. So this is 9. So everyone can see up to 9, I hope. Then I will do 7 minus 9.
Ma'am, could you just scroll up a little?
Yeah. Up to which equation?
Ma'am, till here only. I'm just a second. No, maybe a minute. Minus ME. No, it's okay. So I've subtracted 7 minus 9. Then I can simplify using the expression for EE squared. So ME squared c to the power 4 will basically cancel. So putting E square, C square, 4. What do we get? So we get, so I'm simplifying cos square theta minus 1 to minus sine square. So minus h square u square sine square theta minus 2h square u square cos theta minus 1. So let's see. So I had c square p square. So this also cancels with the e, this term of e square, and this also cancels. So basically, they all cancel among each other, and I only have the remaining terms.
Ma'am, me square c to the power 4 won't cancel.
With this one, sorry,
It's minus.
Sorry. It will be two times. Yeah, it's minus. Sorry. So this is minus c square sine square theta, and I will have minus of 2 then, e square c to the power 4 to EE. So I leave this as EE because it doesn't help me to substitute it. And I can take maybe 2me c square common, and e minus me c square. Okay, fine. So what I'm trying to basically find out is the relation between nu and nu zero. So I want to know how nu changes, okay, depending on this angles and whatever else will remain. So to do that, now I'm going to use, I'm going to use 8 now. So 8 told me that h nu 0 minus h nu is equal to E minus me c square. So I'm going to use that to get the so let me write this using 8. What do I get? So minus h square sine square theta is equal to, so I'm taking this term, the second term on the left to the right, or no, okay, let me just leave it in the left for now. Move it later. No need to confuse you. Oh, so this is the left hand side. Minus c square p square theta 2 me c square, and E minus MEC square is equal to h nu 0 minus h nu. This is from 8. And p square c square can be written as h square nu square sine square theta. So here I've changed this, here I've changed this. Now I'm taking things, changing things between left and right side. Or rather, I'm just cancelling h square nu square sine square theta. So I'm not writing that anymore. So I've got the same term over here. So let me just follow doesn't look nice. So this and this are cancelled. I have 2me c square h nu 0 minus h nu. Now I can cancel an h on all sides and the 2 as well. So 2 can be cancelled, h can be cancelled, and I am left with minus h nu 0 nu cos theta minus 1 m c square nu 0 minus nu. Okay, and now I want to make nu the subject of the formula. So from here I can write nu is equal to nu 0 by 1 minus h nu 0 by mec square 1 minus cos theta. Okay, so this is basically my final relation,
Ma'am, plus
which tells me plus where
1 plus h nu naught by
1 plus. Are you sure? Okay, let me just see. No, I have changed this. So this was cos theta minus 1. Now it's 1 minus cos theta.
ma'am, we will take from the RHS minus nu to the left hand side. That will become 1 plus.
mec square 0. Right, okay. Let me do the step in between. So let's see. So I want all the news on one side. Yeah, that's right. Yeah, thank you. You are right. So this is the
Factor of MEC square.
yeah, sorry.
H mu naught divided by MC square.
Yeah, so this is the final relation. So this tells you how the final frequency depends on the incident frequency and also the angle of scattering. Now this, I have done everything in terms of theta now. So theta was the angle by which the X-ray was scattered from the incident direction. But you can also express, of course, everything in terms of phi. And when you are given problems to solve, then you better be careful about what is theta and what is phi. Okay. So sometimes you might be given phi and not theta. Then you have to use a different relation. So this you can do yourself, I'm sure. Just instead of keeping theta, you keep phi and find a relation again between nu and nu zero. Okay. Now, when you evaluate this, you will always find that nu is smaller than nu zero. So some energy is transferred to the electron, which results in a fall in the energy of the scattered X-ray photon. And if the energy falls, then the frequency falls. So this is what you have to basically know about the Compton effect. And it also verifies. So this was one of the most important experiments which supported the quantization of energy of light as well. So if light can transfer momentum, literally momentum to matter, then it definitely possesses momentum itself. Okay, and since using the relation of momentum with the wavelength of the electron, as Einstein had proposed, you could fit experimental data for the Compton effect. It verified his proposition of that equation, that light has momentum which is related to its wavelength. So this was a very important experiment. And there is one more concept related to the Compton effect which you will encounter, that is called the Compton wavelength. Okay. So this is a sort of convenience. It's just a unit change in a way. So let's see what the definition is. The definition is that the Compton wavelength of a particle is equal to the wavelength of a photon whose energy is the same as the rest mass energy of that particle. So if you have a particle, then it has a rest mass energy, mc squared, where m is the mass of the particle. If you convert this to units of wavelength, then that is called the Compton wavelength. Okay, so E is so if you write hc by lambda, which is in terms of wavelength, energy in terms of wavelength, is equal to mc squared, you get the Compton wavelength. Okay, and why is it useful? It is useful because if the light that is incident on a particle has a wavelength that is of the order of the Compton wavelength of that particle, then you observe Compton effect. So basically, when you have light particles, you will observe Compton effect. And light particles will have a significant wavelength, okay, not very small. So the heavier an object, the smaller its wavelength. Right? So same with the Compton wavelength. So this is just a unit conversion. It's not that significant, but you might encounter it if you have a sum or a problem or something, and maybe instead of the mass, rest mass, you are given the Compton wavelength. So you can modify your relations for the Compton effect again in terms of Compton wavelength. Okay, so that was about the Compton wavelength. We spoke about the hydrogen atom spectra. Yeah?
Ma'am, could you just repeat the last part? I don't know, maybe for me your voice was breaking.
Okay, so I was just talking about the Compton wavelength, so which is basically the conversion of the rest mass energy of a particle into wavelength. using this relation that hc by lambda is equal to mc square. And this assigns a wavelength to the particle, and if you're using this particle in a Compton scattering experiment, then if the incident light has well, at least of the order, the same order as the Compton wavelength, then you observe Compton scattering. So that is what I said. And you might get problems where the Compton wavelength is given and not the mass of the particle. So in that case, you have to be able to write the relations for the Compton scattering in terms of the Compton wavelength. Okay. Then next. So today we will talk about something very interesting, that is wave-particle duality. So what was the evidence in favor of waves having particle nature and particles having wave nature? So what is the hallmark of wave character? So let's say the most significant hallmark of wave character is an interference pattern. So this is in the first experiment over here. You see a simple double slit experiment. You have, of course, all studied this. So when you have light incident on a screen which has two slits, and you let light pass through these slits, then the waves that are going through, they interfere with each other and generate bands of light and dark on a screen in front of the slits, and this is called an interference pattern, right? Now, it was seen that if you have particles, or let's say you would expect that if you have particles, then that there is no concept of interference, so they would simply pass through these slits and form and just hit the screen at two specific spots right opposite the slits. So if it was only particle behavior, so this is wave behavior, this is just particle behavior, what you would expect. And if you normally do an experiment with, I don't know, some blasting sand or something, you would see this. Okay. However, when you use electrons, that is really small particles, then you again end up with a interference pattern. This is the third setup. So interference pattern from electrons. So this is a surprising experiment, that electrons show interference pattern, which would mean that electrons have some sort of wave character. Okay. On the other hand, the two experiments we've been talking of before, the photoelectric effect and the Compton effect, they show that the photons can transfer momentum to matter, such as electrons, which means that they have some sort of particle character. So what we've used to explain photoelectric effect and Compton effect, especially Compton effect, is conservation of momentum and energy during collisions, right? And collisions are a hallmark of particles, not waves. So waves can simply pass through the same space and not collide. They interfere, but they don't collide, right? So what is happening? So we've observed particle nature of waves and wave nature of particles in experiments. So to understand this, let's go back a little bit to how it was discovered in the first place. So the first experiment which hinted at the wave nature of particles is the Davison German experiment. The first experiment which hinted at the particle nature of waves was the photoelectric effect. So what was the Davison German experiment? So Davison and Germer, they were trying to study the surface of a nickel crystal. Okay, and to do this, they were using an electron beam and they were studying the reflected electron beam from this nickel crystal. So they had so the electrons were sent in a sort of collimated beam onto this nickel crystal, and they were scattered by some angle theta, and they had a movable detector which they moved along in an arc for various angles, and they plotted the electron density that they obtained at each angle. Now what they expected, of course, was that they would have some sort of continuous change of electron density with theta. So as they moved the detector like this, they would get either electron density increasing or maybe peaking and falling, whatever, but continuous. Okay. And the other thing I should mention is this electron beam was first accelerated by a certain potential, and they studied various potentials as well. So different energies of electrons. And this was their observation. Okay, the second picture that I have shown. So when it was like
ma'am, your voice is breaking in middle actually.
Yes, ma'am, it's difficult to understand the points. Like,
Yes, ma'am, it's getting distorted somewhat.
okay. Actually, I can hear all of you quite clearly. So maybe it's my internet, but I don't see what I can do. Let's see. So I'll just repeat. Is it better now if I wait for like a few seconds?
Yes,
Ma'am,
ma'am.
if you speak more
I think
loudly.
so. Yes, ma'am. Sometimes your voice seems to be trailing off at points.
Okay, so I'll try to speak more loudly. Let's see. So I was talking about the experimental setup of the Davison German experiment. So they're generating an electron beam which is accelerated by some potential, which imparts, of course, energy to the electrons. And this electron beam hits a nickel crystal and is reflected from it. And they detect this electron beam for various angles theta. Their detector is movable. Okay. And then they plot this electron density for various accelerating voltages across this whole range of theta. Now, what they had expected was that they would get some sort of continuous change in the electron distribution with the angle, and their goal was to find out the structure of the nickel crystal. Okay, so they were not interested in any sort of electron property or wave property or anything. They wanted to know the structure of the crystal. But what they noticed was surprising. So, when they had a low, So when they had a low voltage, like 40 volts, then it was as expected. But then when they increased the voltage, they started getting these sort of strange peaks at certain angles. This they could not explain. In fact, at an angle of about 50 degrees, when the voltage was 54 volts, they got quite a sharp peak. So this is quite a sharp peak and also a second peak in a way. So they were a little bit perplexed at that point. And then, luckily, they attended a conference. So Davison and Germer were in the US, and they attended a conference in Europe where there was discussion about this wave-particle duality. So the wave property of particles was sort of hypothesized, and people were proposing this. And some of these discussions, they used data from some old experiments conducted by Davison and Germer. So not this one. This one was their newest one, which they hadn't published yet. But some of their old experiments were, being shown in this context. So that set them thinking. And when they went back to the US, they started redoing this experiment with a different goal in mind. In the meanwhile, I'm not sure before or after the conference, their nickel crystal had got damaged by something, and the crystal structure was lost. So they wanted to reform it. So they heated it and cooled it, whatever procedure is necessary. And in doing so, they obtained a nickel crystal which gave even sharper peaks. Now, when they studied the nickel crystal further, what they saw was that the nickel crystal was originally a sort of polymorph, I think it's called, where there are like different crystal structures in the same crystal. But after heating and cooling, they obtained a pure crystal. And this pure crystal gave them even sharper peaks. Okay? And from this experimental data with the pure crystal, they wanted to see if what they were getting was an electron diffraction pattern. Now, Bragg had given the relation for diffraction of light long back. So, Bragg's law is basically this, that if you have a gap between slits of D, then you get maxima at points where 2D sine 90 minus theta by 2 is equal to n lambda, n being an integer. So whenever this path difference is integer multiple of wavelength, you get constructive interference and you get maxima. Now, using their data at 54 volts, where they got the sharpest peak, and using this angle at which they got the peak, they found that the wavelength of the electron, so they found that the wavelength of the electron is 0.165 nanometer. Okay, so if they applied Bragg's law to their experimental data, D being the interplanar separations in the nickel crystal, they got the wavelength as 0.165. Now, at a similar point in time, de Broglie had already proposed his relation, which told you the wavelength of a particle given its momentum. Now, this momentum is of course related to the accelerating voltage that they had used. So they knew the momentum of the electrons they were using. And when you calculate the wavelength of the electron from this de Broglie relation, you get 0.167 nanometer. So that is a very, very good agreement. Okay. And this gave them good reason to believe that what they were seeing in the form of sharp peaks was actually an electron diffraction pattern. So the law of diffraction was obeyed. It gave the wavelength of the electron as predicted by de Broglie's relation. So this was a very, very neat sort of completion of the picture of waves and particles. So we now know that waves have particle character as evidenced by photoelectric effect and Compton effect. And now the wave character of electrons was also demonstrated by the Davison German experiment. Now, what was this de Broglie hypothesis? I'm going a little bit back and forth in history, but this was all more or less simultaneous, okay, within a few years of each other. So, what was the de Broglie hypothesis? He said that the particles, moving particles, are associated with wavelengths. So, what was the distinction in our mind between particles and waves? We said that particles are just localized objects which carry energy by virtue of their motion. Okay. And then waves were things which were spread over infinite space, and they were disturbances in the medium. in some form, whether they were mechanical waves or electromagnetic waves. So this was the distinction that we had in our mind. Now, de Broglie changed the focus a little bit. He said, let's say particles are fundamental units. And he distinguished between particles and objects. So he said that objects are large matter, so conventional massive matter. And the particles are fundamental units, so they are small things. And how we experience the behavior of these particles depends on the scale of the phenomena. Okay. So when the wavelength associated with a certain particle is very small compared to its dimension, then we are not able to perceive this wavelength, and we would attribute particle behavior to the particle or matter. On the other hand, if the wavelength is proportional to the dimension or larger, then what we interact with is the wave nature of that object. So then we would say that this matter is behaving like a wave. So de Broglie proposed this, that the wavelength associated with some material object is simply h by p, where p is the momentum of the object. Now, if you're sharp, you'll see that this is basically the same relation as Einstein's relation. He had just said that the momentum associated with a wave is related to its wavelength, and the relation was exactly the same. Okay. But but the implications of just turning the variables around is a lot. So when you apply the second equation, so when you apply the second relation, so Einstein said this was applicable only to waves, and you have a momentum with a wave, then you're just talking about particle nature of waves. If you now accept de Broglie's hypothesis, then the same relation is also applicable to particles, which means that all matter has both wave and particle character. Okay, and depending upon the scale of the phenomena, like I was mentioning, you see one or the other. Now there is now a sort of reclassification of things. It's not just wave and particles. So we are not classifying into waves and particles. We are classifying into fundamental particles and then large combinations of particles. So massive objects and particles. So de Broglie proposed that we talk about fundamental particles which may or may not have mass. So when it has mass, let's say we're talking about electrons, protons, neutrons. When it does not have mass, we're talking about photons. Okay, and they show dual character, being quantum particles. Large combinations of massless particles behave as waves. So when you have a lot of photons moving, so when you're talking about large scale interaction of radiation, then you can describe it as waves. And if you have large combinations of particles with mass, then they behave largely as objects. So he drew this distinction. Now this has again two aspects to it. So there is one situation where you're talking about just the free wave and free particle. In that case, you have to apply. In that case, in that case, you have to apply your judgment according to whether the wavelength is less than the dimension or proportional to the dimension or larger than the dimension when they are free. And when you're talking about interactions, which is what we mostly do in experiments. So you're using the interaction of waves with matter or electrons with light or whatever. Then you have to talk about the scale of the interaction and how the or what it is interacting with. So in these two situations, you have to take your judgment about whether to use wave character to describe it or particle according to two different criteria. When it's free, then you talk about the dimension versus the wavelength, the de Broglie wavelength of the thing. And when you're talking about interactions, then you have to look carefully at what it is interacting with and the energy scale and length scale of the interaction. Now, to put it, like to give you an example, for instance, in the Young's double slit experiment, if you are using, so if the slit widths are comparable to the wavelengths of the electrons, the de Broglie wavelengths of the electrons, then you would observe a interference pattern. If you make the slits too wide, you would see that the electrons give you particle behavior. So you would observe something like the second picture. So then the scale of the interaction is deciding whether you see particle behavior or wave behavior from the electron. Okay. So this was de Broglie's hypothesis, and it worked in the Davison German experiment, and it was accepted. So this is our historical discussion. So now let's try to understand a little more how we can rationalize particles behaving as waves. Now, the most accepted or my favorite explanation for particles behaving as waves is that, or even or waves. This applies to any sort of particle in motion or wave in motion. So everything is a wave packet. Just listen to my arguments, and then we can discuss it if you like. So everything is a wave packet. What is a wave packet? A wave packet is a short burst or envelope of localized wave action that travels as a unit. So it's like a pulse. Okay. And how do you generate a pulse? To generate a pulse, you need a superposition of many waves with phases and amplitudes such that they interfere constructively only over a small region of space and destructively elsewhere. What does this mean? It means that if you want to generate a wave packet at a certain point and have it moving along just as a wave packet, you need to superimpose a large number of infinitely distributed waves. And these waves need to have phases and amplitudes such that you have constructive interference only in a small region and destructive interference elsewhere. So then it will look like a wave packet. Okay. And each component wave function, okay, and now this is a little bit different. So let me first explain this. So if you want to generate this wave packet over here, this first.
No, it is kind of like when Fourier series gives us a specific function, not from the periodic functions interfering with each other.
Yes, it is related to this. Yes. So you're superimposing a lot of infinite waves, which you can say they are the Fourier components, and you're generating this wave packet in one particular region. And these components, they are definitely not in phase. They are out of phase, and they interfere constructively in one place and destructively in other places. Then you get a single wave. Yes. So let me just explain this figure once. Okay. So this rectangle, I don't know what can I call it? Like this purple rectangle. So that is, let's say, the peak of one of the component waves. Okay. One particular component. And that is also moving. So if you go down the figure with time, so the rectangle has moved, it has moved, and it has moved. So the component is also moving. This is one component, remember, and there are many such components which are generating this blue wave packet. And the blue wave packet is also moving. So let's see if we can see that. So let's follow maybe this peak. So this is the 1, 2, 3, 4, 5, 6th peak. And here I have 1, 2, 3, 4, 5, 6. So the 6th peak has moved. Okay. Sorry, this is maybe I counted wrong. So this is 1, 2, 3, 4, 5, 6. And this one. Not counting that one. I hate this. Okay. Let's start here. 1, 2, 3, 4, 5, 6. So this peak of the wave packet has also moved. And then this moves here and this moves here. So both the component and the wave packet are moving. Okay? But they're moving with different velocities, which they have to do in order to maintain the form of the wave packet. So there are a lot of things I will talk about here. So let's just say that if I want to describe a quantum particle as a wave packet, then what would that mean? That if I want to describe the quantum particle, as you know, so I'll move a little bit ahead to explain the concept. You normally would solve a quantum equation, such as the Schrodinger equation, for example. The Schrodinger, remember it's called the Schrodinger wave equation. And you would obtain a lot of solutions or wave functions for that moving object. Now you can think of these solutions as the component waves. And the superimposition of all these solutions for the particle actually gives you the particle as a wave packet. So that is why the quantum equation is called a wave equation. Because the solutions are waves and the superimposition gives you a wave packet, and this wave packet can be identified with a particle. Okay. So that is if it's a quantum particle we're talking about. Okay. But the concept of wave packet is of course general. It has always been there. It's a classical concept. But the analogy is with a quantum particle is when the solutions are the components and the actual particle is the wave packet. Now, depending upon how the components interact, the shape of this wave packet, it may remain constant. In that case, it is called no dispersion. Or this shape may change, and then we say that there is dispersion. Okay? As it moves, the shape changes. In this picture, there is no dispersion because the shape is not changing. However, like I mentioned, the components are moving with a different velocity and the wave packet itself is moving with a different velocity. These have names. So the velocity of each component wave is called a phase velocity. And the velocity of the envelope of wave, so the wave packet itself, is called the group velocity. Okay. All this is classical. So this is, for example, has its origins.
Ma'am, your voice is lagging again. Can you please repeat? Maybe
okay. Yeah. So what I was saying is that the components move with different velocity, and the wave packet itself, or with the superimposed components, that moves with a different velocity, and these have names. The velocity of each component wave is called the phase velocity. The velocity of the wave packet itself is called the group velocity. These terms are not, it has nothing quantum to do with it, okay? these have origins in the physics of sound, etc., the formation of beats and all this. But you can understand the wave particle duality in terms of this wave packet concept. So I am going through this. Okay. Now the wave theory tells us that a wave carries its energy with the group velocity. Now for matter waves, this group velocity can be identified with the actual velocity of the particle. So if you think of a particle moving classically, it has only one velocity. But if you think of it as a wave packet now, which velocity is it? It's the group velocity. Okay? And you can identify the energy E and momentum P of the particle with its relativistic energy mc square, where m is the relativistic mass and its relativistic momentum mu. U is the classical velocity, respectively. It follows from de Broglie's relation that matter waves satisfy this relation. So this is simply the wave relation, that lambda nu is equal to the angular velocity or angular frequency of the wave by the wave constant, and then you use de Broglie's relation to write these quantities, and you end up with lambda nu equal to c square by u. And then you can define a quantity beta, which is u by c. So it tells you the how close the velocity of the particle is to the velocity of light. So when a particle is massless, so if you're talking about photons, then u is equal to c, beta is 1, and lambda nu is then equal to c. If lambda nu is equal to c, that is basically the equation for electromagnetic waves. So the concept of wave packet applies equally well to particles and to light. You simply have to refer to this equation. So here the advantage was that this momentum wavelength relation, whether I call it Einstein's or de Broglie's, it applies to both light and particles. So I could put them on the same footing, and I can describe both light and particles. I can generally call them wave packets. If the wave packet is completely localized, it is a particle. If the wave packet is infinitely distributed, then it is light. Okay, it's a wave. So a wave is by definition infinitely distributed. Now, if you have all the components in phase, then you cannot generate a localized wave packet. The superimposed wave will still be distributed infinitely, and all the troughs and crests will correspond to each other. And this is how light is described. So they're infinitely distributed waves. But if it has to be a particle, then you need the components to interfere and generate a localized wave packet. Now, if you want this localization to be exact, then you have to have this an infinite number of components. Okay. So this you just need to think about a little bit, and this is not a very standard, this is not part of a standard basic quantum mechanics course, I believe, but I think it clarifies a lot about wave particle duality. So I wanted to go over it. And why I want to go over it carefully is because confusion about what this means, the wave particle duality, it remains. So a question of whether light is a wave or light is a particle, for example.
And so, as you said, because the components of lights are infinitely distributed, so we cannot get a localized like a single photon somewhere, because they are detected by in like particle accelerators and all that. They take a single photon or something. So what is that, and how do they get that?
So like I said, so when you are talking about the wave character of whether particles or light, then the wave packet concept is very useful. Okay. But when the phenomena is such that uh, the interaction, so for photons, when there are like very few photons, then they show particle character. So if you have like a single photon interacting with a single electron, such as in the Compton effect and photoelectric effect, and also in your accelerators, as you say, then you see particle character. So then the wave packet concept is not that useful. So the photons, their energy is also indivisible and related to the frequency, right? And that is what manifests itself in accelerators and when light is behaving as particle characters. The wave packet concept is useful when the interaction is wave-like, whether it is for particles or for photons. So we are putting them on equal footing, but like I mentioned before, the way in which we are observing it is still important. So when I say that the light is
Excuse me, ma'am. Yeah,
yeah.
there was a power cut, so I had to leave meeting, ma'am. What were you saying back then?
What was I saying? So you're the one who asked me about particle accelerators and single
Yes, ma'am.
photons
Yes, ma'am.
interacting. Yeah, okay. So what I was saying is that the wave packet concept is useful when we're talking about wave behavior, whether of particles or of light. When we're talking about particle behavior, whether of light or of matter, then the wave packet concept is not so useful. The thing is that, like this was what I started out with, we have reclassified things in a way in which the scale of the interaction, like whatever experiment we are doing, indicates whether the particle behavior will manifest or the wave behavior will manifest. So in an accelerator or the photoelectric effect or the Compton effect, the scale, when you have few photons and when you have small particles, that is when you see, when you have few photons, you observe the particle nature of light generally. And when you have a large number of photons, then you observe the wave nature. So a situation where there are a large number of photons can be treated equally well in the photon picture as well as the wave picture. But when it's a few, then the wave picture is not useful because the interaction is at a particle level. If you are getting my point. So there are two levels to thinking about this. One is that you put, or no, let's say it like this. So our reclassification is now in terms of scale of interaction instead of waves and particles. Okay. It's a bit strange, I agree, but it's so now instead of calling something a matter or wave, we are calling them quantum, non-quantum in a way. So when you have a quantum phenomena, then the particle behavior of light and wave behavior of matter, these sort of crop up, which is not usually there in our experience. Okay, so it's a bit funny, yes. And you will realize in my next slide that it is a very widespread misconception So if you ask the question, is light a wave or is light a particle, and you Google it, let's say, you will come up with multiple explanations, and tables often come up which help to tell you like which phenomena is a particle phenomena and which is a wave phenomena, and you see that they contradict each other. So in one table, I've written the sources here. It says that reflection can be explained in terms of waves and also in terms of particles. But the other table tells you that reflection can be explained in terms of waves but not in terms of particles. So what is the hallmark of waves? So is reflection a hallmark of wave behavior? I would say no. So actually the only one which is consistent and accepted as something that is a hallmark of wave behavior is interference. And here most people would agree that particles do not interfere. And the other one is the interference and diffraction. Okay. And okay, now polarization can be explained with photons, although both of them are no, they can't. Yeah. So you see the second table says that no. Yeah, so polarization, both of them say can be explained in terms of waves but not particles. But here I disagree. Polarization of photons is a very important concept in quantum electrodynamics. So there's a lot of confusion. So these things are not clear in most people's minds, and you do not have a clear guideline over here. So the historically and widely accepted is interference and diffraction. That is something that is called classic wave behavior. And particle behavior is the transfer of momentum, whether it is in the photoelectric effect or the Compton effect. So the difference between the two is basically in one case you have bound electrons and in one case you have a free electron. But they're still basically scattering and transfer of momentum phenomena. Okay, so what I would suggest and how I sort of brought myself to accept wave-particle duality is that we never talk of the thing as a particle or a wave. So we don't say light is a wave, light is a particle, electron is a wave, the electron is a particle. Better to think that the interaction is object-like or wave-like depending on what and how it interacts. So we are classifying the interaction as object-like or wave-like. So that is how I made peace with myself. Maybe that helps you. If not, you can continue thinking about it. No problem. Okay, so there's one more aspect to the dual character of light, which is that do we have a quantum equation for photons? You'll see, we will never touch upon it. In fact, I have my doubts whether you will touch upon it even in your physics courses, if some of you are taking quantum physics. But it is, of course, in principle, possible to have an equation which gives you the wave function of the photon. So let's talk about it a little bit. I'll just read this out. This is just for concept, okay? Don't hit your head over it. So the quantization of the electromagnetic field means that the electromagnetic field consists of discrete energy parcels or photons. Now, photons are massless particles of definite energy, definite momentum, and definite spin. Photons are simply fundamental massless particles of boson character. So this is something you will encounter quite often now as you go on with your courses. So bosons are particles with integral spin, and fermions are particles with half integral spin. Okay, and they follow different statistics, and this leads to different fundamental nature of the wave functions of these particles. So photons also have a wave function, and it would faithfully reproduce all the phenomena involving light in principle. Okay. However, an acceptable model of light which explains everything has still not been established, or at least it's not fully accepted by everyone. Now, the most fundamental let's say the primitive models of electromagnetic field is a lot like the harmonic oscillator model. The harmonic oscillator is simply something, a particle that is vibrating with a constant frequency. And that is the basic model. But of course, there is more to it. And this goes into the field of quantum electrodynamics, which was started by Feynman. And it's continuing, and it's still not fully established. Okay. So we don't have an exact wave function for photons yet. So I would say that since our attempts to understand light in terms of old concepts leads to confusion of whether it's a wave or a particle, what you should just, like I said before, go over to a frame of mind where you focus on the interaction and say, okay, is this wave-like interaction or is this particle-like interaction? And just to be clear now, so if electrons and photons are being treated on an equal footing, where are the major differences? So I'll just list them. So electrons have mass, photons are massless. Photons move at the speed of light. Electrons always move at a speed less than light. Electrons have charge, photons do not. This is a very important thing which we have not talked about. So charge is something that is very unique to particles. Photons cannot have charge, which has very important implications because the principle of conservation of charge is not discarded in quantum mechanics. So that still holds and carries over from classical physics. And because they have charge, electrons cannot be absorbed or emitted as photons. So when we talk about the photon simply being absorbed by an atom and the atom getting excited, this is possible. But for electrons, this is not possible because it would result in a change of charge of the system. So destroying an electron or creating one out of nothing violates the conservation of charge. And although we have a matter energy conversion process.
Yes, ma'am.
Yeah.
From that charge, ma'am, I remember that how will that wave theory explain antimatter? Because from that I remember now when you were saying that, okay, electron positron
Wave
pairs.
theory, yeah, so wave theory, so wave packet theory you mean, or the Schrodinger wave equation?
Wave packet theory.
So there is no problem with antimatter. I mean, there we're not talking about charge at all. I mean, the waves, the component waves, they will all have the same charge as the resultant wave, if you want to talk about the charge. So we are not changing the charge, then it's okay. So it's the same. I mean, you can describe antimatter with a wave packet as well. In fact, you do. So if you have a relativistic quantum equation, then you can describe both matter and antimatter on equal footing.
No, ma'am, I was saying that in that wave packet theory, what difference will we get while explaining positrons and electrons?
Nothing.
Yeah, okay, so because the charge is not accounted for in that theory.
No, it's not accounted for. No.
Okay.
Yeah, but the component wave functions will have to be solved for the same charge as the particle you want to describe. That is there, but other than that, there is no consideration of the charge. Okay, yeah, so I'll just complete this. So although we have Einstein's equation E equal to mc square for matter energy conversion, so far we don't know anything about what charge can be converted into. So charged particles, they cannot be absorbed or emitted. Fine. So this is about wave particle duality. It is more of a concept thing. So you should just understand it, but I will not ask you very deep questions from it. So if you feel a little bit uncertain about it, it's okay. But this is sort of the bedrock of quantum mechanics. So the interesting things lie here. Okay. So as we go along, you'll see things become more mathematical and a little bit less exciting. Those are more like techniques which will allow you to do quantum mechanics. But the fundamentals are in these first few lectures. Okay, now the next thing that I will do today and hopefully complete is the Heisenberg uncertainty principle. You have heard of this, of course, and you have studied this and you know what it is, that position and momentum cannot be exactly determined simultaneously, and delta x into delta px is always greater than or equal to h cross by 2. This is your Heisenberg uncertainty principle. Now, I believe that you would have been taught the same as I was taught, that this is related to measuring the momentum and measuring the position. And why is there uncertainty? It's because when we probe a system, typically with light, we disturb the system, which means we cannot know what its position was or what its momentum was, and etc. Now, this has always bothered me, and I think even in the first 1 or 2 classes, yeah.
Mom, your voice is going low again.
It's going low again. Okay. So let me repeat a little bit. So the Heisenberg uncertainty principle, which you all know, is delta x into delta p is greater than or equal to h cross by 2. H cross being the Planck's constant, reduced Planck's constant. Now, what was the explanation that was offered? I think you must have read the same as I did, that because we disturb a system when we measure it, okay, then our measurement becomes uncertain. Okay, and if we could measure it, then without disturbing it, it would not be uncertain. But this is impossible. So there is always an intrinsic uncertainty. So this was the explanation that I was given, and I had great trouble accepting it because you see, because reality should not depend upon an observer. So this bothered me quite a lot. Okay,
but it arises from that wave packet theory only, no? Because we cannot completely just pinpoint
exactly
on one position.
Exactly. So that is why I actually went through the wave packet theory, which is not normally something that is taught. But I later on I realized that the wave packet theory actually neatly explains Heisenberg's uncertainty principle, and that is how I would like to present it to you here. Okay. Now, how would I explain it then? So a wave packet becomes increasingly localized with the addition of many waves. Like I said, if you want an exact position for a particle, you need an infinite number of waves. But adding many waves of different momenta increases the uncertainty of the momentum, right? So here we cannot add waves of the same momentum because they would have the same wavelength, they would be in phase, and that would not give me a wave packet. So I have to add waves traveling at different speeds if I want a localized wave packet which will travel. And in that case, a wave packet with a very well-defined position will have a very uncertain momentum. Okay. And then it will quickly disperse as well because the faster components move ahead of the slower ones. However, if I construct a wave packet with a very definite momentum, which means a very definite wavelength as well, then it will travel a long distance without dispersing, but it starts out being very broad already in position space. Okay, so this is something like just the electromagnetic wave or light. So a pure wave of a single frequency must be necessarily distributed over infinite space. So see, this is a very neat concept. So it just tells you that since to generate localized wave action, you need a large number of waves of different momentum, then automatically the momentum of this wave packet has a large uncertainty. And if I only have components of a very specific wavelength or a specific momentum, it will give me a resultant of a specific momentum, but this will not be localized. So this cannot be a particle. This will be just a very, or even if it is a particle, it is a very widely distributed wave function, the resultant. So then there is nothing called position. So the wave packet theory is very simple if you think of it in terms of Heisenberg's uncertainty. But this is only a concept, so we have to do the mathematics. So where did Heisenberg come up with the h cross by 2 limit? So this is a bit mathematical. Not all of you will have the background to understand this, but I will mention it nevertheless. So mathematically, a non-zero function and its Fourier transform cannot be both sharply localized. So this is a mathematical requirement. Okay. Now, if I have a function of momentum, then this is a Fourier transform of a function of position. And in that case, x and p are called conjugate variables. So if a Fourier transform of one variable gives you another function of another variable, then these two variables are called conjugate variables. Okay. And they're also non-commuting observable. So you'll understand this a little bit later. You don't have to think of it now. They're also non-commuting. I'm just mentioning it for completeness. This is simply by the mathematics of Fourier transforms. Then, from the same mathematics, you can show that the standard deviation of two conjugate variables, or of x and p here in particular, can be shown to obey this relation. So it comes from the mathematics of Fourier transforms, the limiting value of h cross by 2. So Heisenberg did not just get it out of the air. Okay, and neither did he conduct an experiment to figure out what was the least error possible. He used the mathematics of Fourier transforms because x and p are variables which are Fourier transforms of each other, or the functions of which are Fourier transforms of each other, and they are conjugate variables. And this is the general inequality that all conjugate standard deviation of all conjugate variables obey. Now this h cross by 2 is the particular one for x and p. This is called the Kennard bound in the language of Fourier transforms. Okay. So sigma x and sigma p have an inverse relationship. Since the only requirement was that phi of p and psi of x are Fourier transforms of each other, the uncertainty principle holds for any pair of conjugate variables. So what is the general relation? The general relation for any pair of conjugate variables is that for any two observables q and r corresponding to operators q and r, if that is helpful to you, the generalized uncertainty principle is given by this relation. So the standard deviation square of the two conjugate variables when multiplied with each other is always greater than or equal to 1 by 2i, I is the imaginary number, of the expectation value of the commutator of q and r. So these terms you will understand a little bit later in the next module. So commutator of q and r basically just means qr minus rq. Okay, and this symbol means taking an average. So yeah, so I'm just this is just for completeness over here. I will come back to this. Okay, don't worry. So after the next module by Professor Paul, I will come back to this and tell you how we use this relation. So there is then a generalized uncertainty principle coming from Fourier transform theory, and when you use Q position and momentum as the two operators Q and R, you get the value H cross phi 2, and that gives you the inequality that you're familiar with. Now, the other uncertainty principle that is very important in quantum mechanics is the energy time uncertainty principle, and that is delta E delta T H cross phi 2. This also you must have studied in school before, and then the significance of this was that if delta E is the uncertainty in the energy of that state, and delta T is the lifetime of the state, then these cannot be simultaneously determined. But in case of energy and time, this sounds bad. So what is said is that they have simply an inverse relationship. So if the energy of a state is very precise, then its lifetime is infinite. So the system will not change its state. On the other hand, if the energy is it has a wide range or fluctuating energy, then the lifetime of the state is small. So this is intuitively acceptable, of course, but it does not follow exactly from the Fourier transform relationship. So where do we get this
Ma'am?
from? Yeah.
Yep. And ma'am, that you were saying that the lifetime is very small when energy has fluctuations. So ma'am, this is the reason that why achieving 0 Kelvin is so difficult because of quantum fluctuations.
Yes, you are right. So that it is related to this as well. So then, okay, so what I want to point out is that you cannot derive this relation from the general uncertainty principle relation, simply because firstly, time has no operator, so to speak, and they're also not exactly conjugate variables in the sense of Fourier transforms. Omega and T, of course, frequency and time are, so there is that, but you cannot use this uncertainty relationship. Okay, and I will also come back to this and tell you how to think about this. So I will stop here now. So I have basically completed the introductory or basic part of quantum mechanics, or the concept, and Professor Paul will continue from the next class with more about the postulates of quantum mechanics and also the sort of tools you need, or definitions and tools for handling quantum mechanical problems. So Thursday, are you all having classes on Thursday? So it's Muharram, I saw, so it's officially a holiday, but I
Ma'am, actually, yesterday the state government said that it's on 20th because in Calcutta all the schools are closing on 20th.
Okay, so I don't know if IISER is changing the date or no. So then Thursday we're having a class. Let's just stick to that. If you like, I'll give you a holiday later on. Okay.
Excuse me, ma'am. I had a question from the wave packet part.
Yeah.
Ma'am, does the no dispersion, etc., correspond to some kind of standing waves and normal kind of waves that are moving, or?
Yes. So I have given a link to a video. I forgot to mention that. So there is a link to a video somewhere I put, which is a really, really nice video. It tells you exactly how so it shows you these components and how they superimpose to give you a wave packet, and how they disperse, how they don't. So yeah, so a standing wave would be something that doesn't disperse. Yes. But you can also have a moving wave which is not dispersive. So it's not only
Okay.
the standing wave. Yeah.
So it can be a standing wave, but not necessarily.
Not necessarily.
Okay. Okay. Thank you.
Okay. So you can stop the
Hello,
recording
ma'am.
now. Yeah, yeah, okay.
Uh,
Tell me.
Ma'am, I want to say that the energy is related to the propagation of uh, yeah, the wave is related to the propagation of energy. So how could a particle can create wave? Is it like the particle in microscopic level convert it to vanish its mass and convert it to energy by Einstein equation E is equal to mc square, and then it propagates?
No, no, no. It remains. Its mass remains. Its mass does not go away. Its kinetic
How could a mass
energy.
create a wave? We know that wave does not have any mass or charge.
So the energy of the particle is just its kinetic energy. Let's say. Okay. So that the rest energy that is converted to mc squared, that is there. That is intrinsic to that wave. In addition, the kinetic energy part is represented as a wavelength. I mean, a moving particle is associated with a wave. When it comes to rest, it's still a particle.
But from the physics, I know that the wave is the propagation of energy. Y means the oscillation of particle of its medium, or oscillation of field, like electric or magnetic field. So how kinetic energy can oscillate and propagate as wave?
So you have to sort of get rid of this concept. So the thing is that, okay, let me just go one step back. So it is, if light is just transmitting energy, like in the classical theory, then even light as photons, you cannot convert light to photons. So in the photoelectric effect, remember, then if the electron wanted energy, it just needed to wait for sufficient energy to get transferred to it, and then it would get emitted. But that doesn't happen. So so the whole concept changed, that the wave carries energy also through its frequency or its wavelength. So these particles of energy are also indivisible. So this is for the light. Now, when you come to particles, again, it is the same thing, that the energy of the particle is indivisible. It only moves. So you're not. So it's an intrinsic energy. It is not being carried from point A to another. So the particle itself is a wave. So it's not creating a wave. If you understand. So the you can say that this particle is
So
moving
it is
around
a
or
type of
vibrating.
different type of wave.
It is a different type of wave. Yes, yes.
Okay.
It certainly is not disturbing the medium. So it's not a mechanical wave, and it is also not an electromagnetic wave. It is a probability wave. So the
Okay, ma'am.
particle itself is moving to generate this wave, if you want to think of it like this.
Like it is a new concept of wave.
It is a new type of wave, yes. It's called a matter wave.
Ma'am,
Yeah.
hello.
Yeah. Yeah. Please
Ma'am,
ask.
somewhere I studied that if in the young double slit experiment, if we put a detector to measure which electron is going from which slit, then the electron behaves as a particle, and if we remove the detector, then it just behaves as wave. Is that true? I mean,
Uh, yes. So again, for electrons, if you're treating them one at a time, as you would if you detected it, then it behaves like a particle, because what you get as an interference pattern is not of well, no, let's say how to put it. So this waves, so you will understand this when we talk about superposition of waves and eigenstates. So the collapse of a wave function into an eigenstate would make it behave like a particle in a way. So the probability distribution gets collapsed. So okay, so just remember your question. I will come back to it after we've done the postulates of quantum mechanics. You are right. This is a proper observation. Yes. It's a very strange observation, but it can be explained. Okay. Any more questions today? Okay. Fine. Thank you, everyone. I will leave the lecture today.